EU strategy to harness the potential of offshore renewable energy for a climate-neutral future declares that technological and physical potential of offshore renewable energies is crucial if Europe is to achieve its carbon emission reduction targets for 2030 and become climate neutral by 2050. And it has established the objective to have an installed capacity of at least 60 gigawatts of offshore wind by 2030. This will require overcoming a number of obstacles and ensuring that throughout the supply chain, all players can both accelerate and sustain this increase in deployment rate. One of the main optimization obstacles that offshore wind faces is the cost of operation and maintenance activities, especially because of the difficulties associated with access for maintenance. A wind turbine is composed of many components, such as coupling and transmission systems, the gearbox, lubrication systems, the generator, rotor and yaw brakes, cabling, power conversion, bearings, the tower and foundation, the hub and the pitch system. Among all the systems, the hydraulic pitch is critical for the functionality of the offshore wind turbines, as it is responsible for the input wind power control by regulating the pitch angle of the blades. Its relevance in the reliability of wind turbines justifies the design of a data monitoring and analysis system to increase the probability of detection of critical failure modes. The project Digitalization of Critical Components in Offshore Wind Turbines, Docc-Off, has developed a digital platform that captures and manages data from the monitored components and can reduce the impact of the hydraulic pitch system failures.
As component developers, the main reason to digitalize our component comes from the side of gaining knowledge of the real functioning of the hydraulic system in operation. The failure mode, effect and criticality analysis of a generic wind turbine hydraulic pitch system carried out in the framework of Docc-Off identifies critical failure modes and proposes monitoring-based mitigation strategies. As a result, cylinder friction and leak detection, pump flow rate and accumulator pre-charge estimation have been selected as priority to monitor.
In this project, a guided analysis of hydraulic pitch system is offered in a user-friendly digital platform. It focuses on a selection of the main failure modes already identified, where both availability of data with commercial sensors and relevance of their detection have been taken into account. As a result, the analysis of hydraulic pitch system, as well as the detection of anomalies on it, are provided to wind farm operators.
Docc-Off has developed a specific digital platform to monitor hydraulic pitch system health. Wind farm operators will be able to monitor the wind farm using the map screen. Whenever a potential issue is detected, the wind turbine's icon will change its color. Clicking on pitch system health, its evolution will be shown. Hydraulic system flow health, cylinder speed, and cylinder accumulated flow differences are plotted for each blade against failure regions. If any of them fall into a potential failure zone, maintenance is recommended. In addition to that, specific variable analysis is available. The partners have tried their algorithms on synthetic data from a high-fidelity simulation model with good results, and they had then tried them on sensor data from a scale prototype in the lab. The scale prototype is mounted on a test bench, where it moves as on a wind turbine, while it is opposed by another cylinder which applies the force it would face on a wind turbine. The prototype is equipped with needle valves to cause leaks between the cylinder chambers, as well as at the pump. By running hundreds of tests where the prototype moves with different turbulent wind inputs, Docc-Off partners get the sensor signals to have the same overall statistical properties as they would on a wind turbine. Only here they get to easily cause leaks. They have thus observed that the effects of the leaks on sensor data are as predicted by their model, and that their algorithms work as well on sensor data as they do on synthetic.
In this project, we have been developing strategies to validate the digital platform both in lab and on real wind turbines. We collected the requirements of a full-scale demonstration campaign in real operating conditions, such as turbine location, instrumentation, and data transfer. This demonstration is the logical next step to implement the digital solutions into actual wind farms.
The most relevant impacts in specific needs of the offshore wind energy sector are increased component reliability and reduced failure rates, O&M smart decision-making benefiting every stakeholder in the value chain, improved wind farm performance and reduced levelized cost of energy, tool development with clear exploitation potential in the offshore wind sector, strengthened European industry base with digital and data analytics skills.
Docc-Off is a perfect example of a successful cooperation project between European companies from the offshore wind value chain. The partners in Docc-Off have achieved unique competitive advantages by developing a condition monitoring digital platform that is expected to be implemented in the next generation of offshore wind farms. Moreover, Docc-Off results can be scaled up to other critical systems in the wind turbines, enabling this way further market opportunities for the European industry.